This is module 15 on number theory. And I had mentioned yesterday, or mentioned when we were talking about the last two modules, that Pierre de Fermat would be a key player in number theory, and he is. So let's move over to the PowerPoint and talk through the contributions of Fermat to number theory. So here we go. And there will be just a few notes to add to this one. Come on. I mentioned the French triumvirate the last couple of modules. Same three guys, Descartes, Fermat, and Pascal. And in the last module on probability, Pascal and Fermat were the two people who were working together to lay the foundations. On the module before that, Fermat and Descartes worked together to form the foundations for analytic geometry. And we've got Fermat working by himself. Well, not working by himself, but Fermat is the main person we're going to talk about for the foundation of number theory. Fermat was not a professional mathematician and really didn't get started on it very seriously until after he was 30 years old. He is known as the Prince of Amateurs because he was the amateur in the group. He didn't do this for a living. He wasn't a professional mathematician. He had another job. He was a civil servant, and that was the job that paid the bills. But we've already mentioned his work with Descartes, and that work helped to lay the foundations for calculus. His work, we talked about the pseudo equality method. We talked about probability, but his work with number theory really put him on the map and really overshadows everything else that he did. He was a member of this priest's circle of mathematicians in Paris. This is Father Morin Mersenne, and we're going to see his name again in just a few minutes. But he was an important, again, an amateur mathematician. He was a Catholic priest, but he was very interested in scholarly activity. And so he had this group of people who met in his home. I don't know how often, but every now and then. They were scholars, they were mathematicians, philosophers, scientists. They were from France, but then as people from other countries would travel through France, they would also visit this group and share their ideas. Fermat, as an amateur, didn't have to record, didn't have to publish. I don't think it was quite like it is today, way back then, but he didn't publish what he was working on. He didn't write books. He didn't write journal articles. He wrote letters to other mathematicians, and we do have those letters. We've got journals that he's kept. We've got some notes that he made in books, but we don't have any published materials from this time. The only published paper, well, actually, we've only got one, the published paper in 1660. And even on this one, he didn't use his name. So he wasn't publishing it in a way to get his name out there and to make a name for himself. He refused to perfect his ideas, so they never were ready for publication. So he didn't want to put in that extra effort that needed to be there to actually make it worthy of publication. He didn't go back and polish all of his theorems. He didn't put the finishing touches on problems that he solved. In fact, in this next bullet, when he corresponded with contemporaries and introduced some of his latest results, frequently they were met with challenges, and other mathematicians were annoyed with him because they wouldn't answer the challenge, or he would not answer their communications. So he would frequently just drop off and not deal with anything else. He would raise questions, he would pose problems, but not engage in the discussion that ensued after that introduction. So number theory, the history of it goes all the way back to the ancient Greeks. And if you'll remember, the Pythagoreans believed that all was number, and the Pythagoreans looked at properties of numbers. Euclid had some elegant solutions or elegant proofs to some number theory theorems. in Euclid's Elements. So remember, it wasn't just about geometry, it was also about number theory. And in his Elements, he defined prime numbers and composite numbers. So just to remind you what those are, a prime number is a number that has only two factors, and those two distinct factors are the number itself and the number 1. A composite factor has more than two factors. So as a result of those definitions, the number 1 is neither prime nor composite. Factors of a number are those numbers that divide into the number. So if x is a factor of y, then there exists some other number a so that x times a is equal to y. Or you could say y divided by x is equal to a. A proper factor, and this is important in the definition of a perfect number, a proper factor is a number that's a factor other than the number itself. So a perfect number is a number that's equal to the sum of its proper factors. So the first perfect number that we've got, let's come over here and just look at two of these really quickly. Take a look at the number 6. Well, 6 has as its prime factors the numbers 1, 2, and 3. And I should say not prime factors. That's not what I meant. I meant proper factors. Too many P words here. The proper factors of 6 are 1, 2, and 3. 6 itself is not considered a proper factor. And 1 plus 2 plus 3 is equal to 6. So that means that 6 is a perfect number. The next perfect number is the number 28. And if we look at the proper factors, we get the numbers 1, 2, 4, 7. 4 times 7 is 28. 2 times 14 is 28. 1 times 28 is 28, but 28 is not a proper factor. And 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus that 14 right there is 28, which means 28 is a perfect number. Well, as you can imagine, it doesn't seem like there are very many of them. So let's pick a number between 6 and 28 and see what happens. Let's take the number 12. All right, we need to look at the proper factors. Proper factors of 12 would be 1 times 12, but 12 won't count, 2 and 6, 3 and 4. Let's add those numbers together. 1 plus 2 is 3, plus 6 is 9, plus 3 is 12, but then I've still got to add 4, which is 16. I got a number that's bigger than the number that I started with. And when the sum of the proper factors is greater than the number you started with, this is called an abundant number. So 12 is an abundant number. If the sum of the proper factors is greater than the number itself, it's an abundant number. It's just full of factors. The factors are abundant. Okay, well, you could guess some of the numbers in here that are not abundant. Prime factors, well, a number that's prime, like 7, its only proper factor is 1. So certainly prime factors are not going to be proper numbers. They're certainly not going to be abundant numbers. What about 15? Well, the proper factors of 15 are 1, 15 doesn't count, 3 and 5 count, and that's it. And the sum of those numbers, 1 plus 3 plus 5 is 9. Well, that's too small. It's less than 15, so it's not perfect. It's not abundant. It's not big enough. So this is called, so in this case, when the sum of the proper factors is less than the number itself, this is a deficient number. 9 is a deficient number. It means it just doesn't have very many factors. And it isn't always that you've got to have a whole bunch of them. It's just that you've got to have enough that they add up to be greater than the number itself. And it doesn't matter how much bigger than the number itself, just greater than. Okay, well, these ideas go all the way back to Euclid. Euclid defined perfect numbers in Euclid's Elements. Let's go back over to our PowerPoint. And I think this was there we go. That's it. Oh, I left out one. So we've got perfect numbers, we've got deficient numbers, we've got abundant numbers, but sometimes we talk about two numbers at a time, and they are called either friendly or amicable numbers. So a pair of numbers is friendly. I'll use that word if the sum of each's proper factor is the other number. Okay, the example here. All right, so let me draw a line, and we're talking about friendly numbers here. We're going to look at 220 and 284. So the proper factors of 220 and 284 are 1, 2, I'm going to write the sum like this, 2 times 110, 1 times 220 is 220, but 220 is not a proper factor. And then I've got 4 times 55, so 4 plus 55. And then I've got 11 plus 20, 5 plus 44, 10 plus 22, and I think that's it. 1, 2, 4, 5 and its partner, 6, 7, 8, 9, 10 and its partner, 11 and its partner, and then we start getting the other halves of the partners. When you add these numbers together, you get the number 284. Okay, well, let's take 284 and write down its proper the sum of its proper factors. 284 is 1 times 284. We just take the 1. It's 2 times 142. So let's add 2 and 142. It is 4 times 71. So 4 times 71, and that's it. Those are the only factors of 284 besides the number itself. And when I add those together, I get 75, 217. No, that's not right. 203. Let me start at the beginning. 1 plus 2 is 3. 145, 149. Did I leave one out? Oh, I'm not trying to add up to 284. I'm trying to add up to 220. That's right. So that does add up to 220. So the sum of the factors of 284 add up to 220. The proper factors of 220 add up to 284. Therefore, 220 and 284 are friendly numbers. Well, think about how you would find other pairs of friendly numbers. It's not like finding one number at a time. You've got to try a number, add up all its factors, and then take and see what you get, and then see if that sum's factors add up to the number you started with. We don't have a whole lot of them. Fermat came up with a pair. Fermat figured out that 17,296 and 18,416 are friendly numbers. Descartes figured out that 9,363,584 and 9,437,056 are friendly numbers. Wow. I just can't even begin to think about how he figured that out. But there's another pair of numbers that was found after these two that's a much smaller pair. And in 1866, which is after both of these guys, remember they're in the 1600s. In 1866, a mathematician named Paganini figured out that 1,184 and 1,210 are friendly numbers. And you are certainly welcome to check out those pairs of numbers whenever you wish. That's pretty impressive to do that arithmetic and figure that out. Okay, so let's go back to the PowerPoint. So all of this work with perfect numbers is really important because now the search is on for perfect numbers. This becomes a problem that's going to drive what's going on in number theory for many, many years. And the ancient Greeks actually knew the first 4 perfect numbers. They knew that 6 and 28 those were easy to check. 496, that doesn't take you all that long either. 8,128, it takes you a little bit longer, but those are the first 4 perfect numbers. So the mathematician Neomachus, who was one of the later Greek mathematicians, looked at those 4 numbers and he said, well, I see some patterns there. And you take a minute and see if you see some of these same patterns. See what you see. Okay, well, the first thing he noticed was the last digit in those numbers. It's either a 6 or an 8. And he noticed that they alternate. It's 6, 8, 6, 8. And so he conjectured that that's going to continue. That perfect numbers are going to continue in that pattern so that the last digit alternates between 6 and 8. Of course, when they're written in order. Also, if you look at those numbers, the first number is a 1-digit number. The second one's a 2-digit number. The third one is 3 digits. The fourth one is 4 digits. And he said, well, I'll bet the next one's going to be a 5-digit number and then a 6-digit number and 7-digit and so on, so that the nth perfect number has n digits. His next conjecture actually just comes right as a result of the first one. If they all end in a 6 or an 8, certainly they're all going to be even. Of course, we may find out somewhere down the road that they don't all end in 6 or 8, but they could all still be even. Then he gets a little bit more technical. And he says, every perfect number is of this form. Every perfect number can be written in the form 2 to the k minus 1 times 2 to the k power minus 1. For some k, some natural number k greater than 1, where 2 to the k minus 1 is a prime number. So he's saying every perfect number is going to look like this. So this is going to help me generate, this is going to help me find those perfect numbers. Also, if this is true, then it's certainly true that the conjecture above that is true. Because if every perfect number can be written in this form, well, a power of 2 is one of the factors. So of course, the numbers are going to be even. He also said that there are infinitely many perfect numbers. Okay. Kind of seems like that might have been obvious, but maybe not. All right, so this is Neomachus. This is pretty early on. He lived from 60 to 120 of the Common Era. But this is what's going on with number theory, this work with perfect numbers. Well, mathematicians continued to look for perfect numbers. So this Islamic mathematician, Ibn Fallas, who lived from 1194 to 1239, knew about those four, but he found some more. And so he wrote a short book, and he included the fifth, sixth, and seventh. And he said the fifth one is 33,550,336. There's the sixth one, and there's the seventh one. All right, so those are the next three. What's that tell us about? Oh, and he included three more, but it turned out they were not correct. So let's look at those three that we know are correct. The fifth one, the sixth one, and the seventh one. What does that tell us about Neomachus conjectures? Well, remember Neomachus said they went 6, 8, 6, 8. So the fifth one should end in 6. The sixth one should end in an 8. Oops, didn't do that. I had a 6, 6, 8. So at this point, I would need to change my conjecture to no, they don't alternate between 6 and 8, but that last digit is always either or 6 or an 8. I'd be willing to stick with that. Now, his second conjecture was that the nth perfect number had n digits, which meant that the fifth perfect number would have 5 digits. It would be in the 10,000s. Well, this one's not. This one has 8 digits. So that's not true. But these other conjectures, well, we're still trying to figure out if those are all true. Those are still open-ended questions that we're still working on. Okay, Euclid in his Elements had a theorem about prime numbers, and it sounds very familiar to that one of Neomachus. He said if 2 to the n minus 1 is a prime number, then this product is prime. Well, that's not exactly what Neomachus said. Neomachus said that every prime number is going to look like that product right there. Euclid said, I can use this 2 to the nth power minus 1 to generate as many prime numbers as I want. I just have to keep checking. It's a whole lot easier to check and see if 2 to the nth power minus 1 is prime than to see if this product is perfect. So that was a really important theorem and step forward. And we could check that out. Let me write this theorem down. If 2 to the n minus 1 is prime, then 2 to the n minus 1 times 2 to the nth power minus 1 is perfect. Let's see what we get. Oh, didn't want to stop it altogether. Okay, so let's suppose n is equal to 1. Well, if n equals 1, I've got 2 to the first power minus 1, which is 2. Well, that's not prime, so this theorem doesn't apply anyway. No big deal. N equals 2. 2 squared minus 1 is 4 minus 1, which is 3. Yes, that's prime. My hypothesis is true. So what about 2 to the 2 minus 1 times 2 to the second minus 1? What do I get? Well, 2 minus 1, the exponent is 1. So this is 2 times 2 to the fourth is, I'm sorry, 2 squared is 4 minus 1 is 3. 2 times 3 is 6. Sure enough, it's perfect. Okay, there's my first perfect number. What if n is 3? Well, if n is 3, 2 to the third minus 1 gives me 8 minus 1, which is 7, which is a prime number. So we're going to check 2 to the 3 minus 1 times 2 squared minus 1. 2 to the 3 minus 1 is 2 squared times 4 minus 1. So that's 4. No, this should be 3. So this is 8 minus 1. So I've got 4 times 7, which is 28, which is my second one. And so if I've got if n is 4, 2 to the 4th is 16 minus 1 is 15. That's not prime. What about n equals 5? Well, 2 to the 5th is 32, and 32 minus 1 is prime. So what about when n equals 5? Well, that would give us 2 to the 5 minus 1 is 4 times 2 to the 5th minus 1. So that's 16 times 32 minus 1 is 31. 16 times 31, 1648 is 496. And that was my next perfect number. Now, certainly this isn't a proof, but what I'm trying to do here is just illustrate how this theorem works and illustrate how it helps us to generate perfect numbers. What I don't know is, does this generate all of the perfect numbers? That's what's missing from the theorem. Okay, so let's go back. All right, so for which values of n? So a new problem then would be, in Euclid's theorem, which values of n make that hypothesis true? For which values of n is 2 to the n minus 1 a prime number? So Mersenne, remember the father, the priest, as in priest, Morin Mersenne, is also engaged in this work with prime numbers. And he's working on this 2 to the nth power minus 1. And so they decide to call any number that can be written in the form 2 to the n minus 1 as a Mersenne number. So even these numbers that we crossed off that said would not give us prime numbers, like 2 and 15, they weren't prime, but they are Mersenne numbers. Okay, so I'm going to write that down so it will be in your notes when we come over here. 2 to the 4th minus 1 is 15. This turns out it's not prime, but it is a Mersenne number. 2 is a Mersenne number. All of these prime numbers over here that we got, they're all Mersenne primes. So not every prime number is a Mersenne prime. 11 is not. 17 is not. So there are plenty of prime numbers that are not Mersenne primes. Mersenne prime numbers are those that are one less than a power of 2. And so Fermat started working on this problem. Remember, he's going to these meetings and he collaborates and he corresponds with Mersenne an awful lot. And so he starts working on this problem about, well, how can I predict when 2 to the nth minus 1 is going to be a prime number? And so he communicates with Mersenne about 3 of his ideas. And of course, he doesn't prove anything. But here are those 3 ideas. He said, if n is not prime, then 2 to the n minus 1 is not prime. Okay. So in other words, I don't need to worry about looking at any value of n that's a composite number. Restrict my search to values of n that are prime. Again, he didn't prove it. And it's pretty easy to prove if n is even, because you're just factoring the difference of the difference of 2 squares. It's not that much harder to prove if n is not even. It's a factoring problem. Okay, if n is an odd number, I meant. If p is an odd prime, all right, and that means everything but 2, actually, because 2 is the only even prime. If p is an odd prime, then 2 times p divides 2 to the p minus 2, or p divides that expression, 2 to the p minus 1 minus 1. And then his third conjecture is if p is an odd prime, and again, that's everything but 2, then the only possible divisors of 2 to the p minus 1 are 2 times pk plus 1. Now, this is important because if we're looking for perfect numbers, we need to think about the factors, the proper factors of those numbers. And remember, we said what Euclid said, if 2 to the n minus 1 is prime, then that product right there is perfect. Well, 2 to the n minus 1 is one of those factors. So it would be one of the proper factors. It will be important to identify the proper factors of these numbers when I'm working with perfect numbers. Okay. So all of this work is really interesting that he's doing. He's not always finishing the work. He's making really good conjectures. I mean, he's got the mind of a mathematician, maybe not the persistence, because he doesn't, or the drive. He doesn't have the drive to sit down and muscle out the proofs that you need. Okay. He is probably most well known for what's called Fermat's last theorem. And this was a note that was found after his death by his son. And he wrote it in the margin of one of his books. So after he dies, his son goes to his office, his study, and is going through his books, and he finds his copy of Arithmetica. Remember, that's Diophantus' book. So Fermat recognized the importance of this book. He kept it and he worked through it. He worked all those problems just like we worked a lot of them. In that book, he wrote a note in the margin, and he said, it is impossible to write a cube as a sum of 2 cubes, a fourth power as a sum of 2 fourth powers, and in general, any power beyond the second as a sum of 2 similar powers. For this, I have discovered a truly wonderful proof, but the margin is too small to contain it. So in the margin of the book, what he's saying is, this is writing it out using symbols. If n is greater than 2, then x to the nth power plus y to the nth power equals z to the nth power. That equation does not have any solutions. Now, if n equals 2, there's your Pythagorean relationship. But for n greater than 2, that's your cubes, your fourth powers, fifth powers. There are no solutions to that equation. He wrote this in 1637. And he said, I've got a proof. I can prove it. I just don't have room to prove it in this tiny margin. Well, people took that, and the challenge was on to find the proof of this theorem. I mean, it's so easy to understand. And it seems like shouldn't it be a walk in the park after we have found so many different ways to prove the Pythagorean theorem? Just to take this up a notch? Well, no, not really, because people worked on it for years and years and years and did not come out with a proof of that. In 1976, now how many years after is this? 1976, we're talking 340 years later. This was shown to be true for all exponents up to 125,000 with the use of a computer. So a computer generated proof with quotation marks around it only for n up to 125,000. And then in 1983, the equation was proved that it only has a finite number of solutions. So if it does have solutions, there are only finitely many. But then in 1993, the mathematician Andrew Wiles, who was a mathematician from Princeton who was visiting at Cambridge, and while he was there in 3 lectures, he sketched out his proof of this theorem, and it was earth-shattering, groundbreaking. As it turns out, in those 3 lectures, there were some missteps. So there were some flaws in his proof. And he went back and worked on it for the next 2 years. He spent the next 2 years of his life working on that proof. And in 1995, published the final proof in the Annals of Mathematics, which is pretty much known as the best of all journals in mathematics in the world. When he did that, his picture was on the cover of Time magazine. He was on nightly news. I remember seeing his picture on CBS News that evening when it had been published, and they made the announcement that the proof had finally been done after over 300 years. Well, if you think back about those 3 ancient problems of antiquity, it took much longer than 300 years to prove that they could not be done. So it's no surprise. 300 years in the grand scheme of things isn't all that long. But if you get a chance, Google on Andrew Wiles. In fact, go to YouTube and Google and search on Andrew Wiles. There are several interviews with him, and it's such a pleasure to watch him talk about this. And he gets teary-eyed talking about the beauty of mathematics and what this meant to him. It wasn't just, oh my gosh, I'm the greatest mathematician in the world, but the enormity of it and what he had done was just really overpowering. So really and truly, take a look at that on YouTube when you get a chance. Okay. There is still work continuing to be done in number theory, and many applications of number theory today, in particular with coding, with not coding as in writing computer programs, but coding as in secret codes in terms of things like your credit cards, passwords, all those kinds of things. Every time you hear about some bank or some company has been, what's the right word? Violated is the word I'm thinking of, but that's not quite right. When they've been breached, something's been messed up. And so what happens is they bring in the mathematicians and the people with this kind of mathematical knowledge to build this code so that happens less frequently, we hope. Those of us who have a pocket full of credit cards certainly hope it doesn't happen very often. All right, so the next one is on attempts to prove the parallel postulate, and I'll see you there. Take care. Bye-bye.